So, welcome to our online chemistry class. Our topic is solutions. Let us discuss chemistry under this solution topic under part number 2. So, in this part, we will discuss the Henry's law. So, all are familiar with that. As we increase the pressure of gas in a liquid, then solubility of that gas increases. So same thing can be explained under this law. So what is the statement? Henry's law stated that the solubility of gas in a liquid is directly proportional to the pressure of the gas over the solution. Thus, same statement can be expressed in mathematical way. S is directly proportional to P, or S is equal to KH into P, where S is the solubility of gas in mole per liter, P is the pressure of the gas in bar over the solution, KH is the proportionality constant, is called as Henry's law constant. Now, to get the unit of KH, we have to rearrange equation 2.1. So KH is equal to S divided by P. The unit for solubility is mole per liter and that of pressure is in bar. So what is the unit for KH? It is mole per liter per bar. Now if we substitute pressure is equal to 1 bar, then what is the KH? KH is equal to S. Thus the KH is the solubility of gas in a liquid when its pressure over the solution is 1 bar. Now we have to see the application of this Henry's law. So before sealing the bottle of soft drink, it is pressurized with a mixture of air, CO2, saturated with carbon dioxide. That CO2 means carbon dioxide saturated with water vapors. Because of high partial pressure of this carbon dioxide, its amount dissolved in that soft drink is higher than the solubility of CO2 under normal condition. So when the bottle of soft drink is open, excess dissolved CO2 comes out with effervescence. So when you have to remember the Henry's law, the key point is the soft drink. Okay. Now next is exceptions of Henry's law. So exception to Henry's law, under this we have to discuss the two gases like ammonia NH3 and carbon dioxide CO2 do not obey the Henry's law. The reason is that these gases react with water. So let us see the reaction. NH3 ammonia react with water and it will give. So it accepts the proton H plus from that water because the nitrogen of ammonia contain a lone pair of electron, non-bonding pair of electron, and that accept the proton H plus. So according to Lowry-Bronsted acid-base concept, ammonia is proton acceptor, so it is a Lowry-Bronsted base and it will produce NH4 plus, which is a conjugate acid of the ammonia. At the same time, water donate the proton, so it is Lowry-Bronsted acid and its conjugate base is the OH minus. So the difference between conjugate acid and its base is of H plus, that is proton. At the same time, these two NH4 plus and OH minus, ammonium cation and hydroxide ion respectively, they also combine together and they produce ammonia and water back. So there is an equilibrium between your ammonia and water with ammonium cation and hydroxide ion. Similarly, we can observe the reaction of carbon dioxide with water, and it will produce carbonic acid. So here water again donate the proton to CO2 and it will produce H2CO3, carbonic acid. And again that carbonic acid undergo decomposition into carbon dioxide and water. So because of these reactions, ammonia and carbon dioxide gases have higher solubility than the expected by the Henry's law. So these are the exceptions. Now next is the numerical based on this Henry's law. So one numerical is in front of you. Calculate the solubility of gaseous oxygen in water at a temperature of 293 Kelvin when the partial pressure exerted by O2 is 1 bar. So to solve this numerical, you must know the given things. So here this temperature is mentioned 293 Kelvin, so unit is Kelvin. Then partial pressure is mentioned of that oxygen and it is 1 bar. P is equal to pressure of that gas is equal to KH into S. So how do you rearrange for S? S is equal to P divided by KH. So formula is not mentioned here, you can write down in your notebook. S is equal to P divided by KH. So P is 1 and KH is equal to 34,840 mole per liter. So what is the answer? It is 2.87 into 10 raised to minus 5. Solubility unit is moles per liter. Therefore, the solubility of oxygen in water under the given condition is 2.87 into 10 raised to minus 5 mole per liter or molar. Capital M means molar. Molarity is mentioned here. Then next is the value of KH for carbon dioxide at a temperature of 293 Kelvin is 1.6 into 10 raised to 3 atmosphere liter per mole. At what partial pressure would the gas have a solubility in water of 2 into 10 raised to minus 5 molar? So what is the given thing? Henry's law constant is given 1.6 into 10 raised to 3 atmosphere liter per mole, and solubility is mentioned here in water, it is 2 into 10 raised to minus 5 molar. So what is the partial pressure? You have to write according to Henry's law or as per the Henry's law formula. Write down the formula with respect to your pressure. P is equal to KH into S. So KH is 1.6 into 10 raised to 3 and S is 2 into 10 raised to minus 5. So multiply, so we get 0.032. Don't forget to write the unit. So this liter per mole and mole per liter get cancelled. Unit is atmosphere. Okay. So what is the partial pressure? It is 0.32 atmosphere. Now next concept that we have to discuss is vapor pressure of solution of liquids in liquids. So to discuss this concept, to find out the vapor pressure of liquid-liquid solution, we have to consider two components A and B, and these two volatile liquid solutions having these two liquid components, we name them as A and B. Then When we place a volatile liquid with their components in a closed vessel, we find that equilibrium is established between liquid phase and the vapor phase. Then how do you write the total pressure? It is represented by P total, and it is nothing but vapor pressure at an equilibrium state. Then we have to mention the partial vapor pressure of that component A is equal to PA and that of B is PB respectively. While the mole fraction of component A is XA and that of B is XB. Okay. So to evaluate the vapor pressure of volatile liquid, we use one law, and that law is called as Raoult's law. So let us discuss Raoult's law. So first we'll state the law. So Raoult's law states that in a solution, the partial vapor pressure of any volatile component of a solution is equal to the vapor pressure of pure component multiplied by its mole fraction in the same solution. So your statement should be correct. Don't change the wording. Then suppose that for a binary solution of two volatile liquids A and B, PA is the partial vapor pressure of that A and PB is the partial vapor pressure of B, while XA is the mole fraction of A and XB is the mole fraction of B component in the same solution. Then according to the Raoult's law, what we write? PA is equal to XA into PA0. Okay, while PB is equal to XB into PB0, where PA0 and PB0 are the vapor pressure of pure liquids A and B respectively. PA and PB are partial pressure, and if not is written or 0 is written, then it is a vapor pressure of that pure component. Okay, and PA and PB are the partial pressure of that component in the solution. Then according to Dalton's law of partial pressure, the total pressure P above the solution is P is equal to PA plus PB. So if we substitute the value of PA and PB by using this Raoult's law, so to write P is equal to PA0 into XA plus PB0 into XB. Then we know that the sum of mole fraction of the component in the solution is always equal to 1. So XA plus XB is equal to 1. So what you write? XA is equal to 1 minus XB. Then the above 2.2 equation can also be written by substituting the value of XA in that equation 2.3. Here substitute XA is equal to 1 minus XB here. So what we get? PA0 as it is, XA is equal to 1 minus XB and plus PB0 into XB remain as it is. Then if we rearrange that equation, what we get? If we multiply PA0 in bracket, so PH0 minus PH0 into XB plus PB0 into XB. Now take XB, which is common outside the bracket, then what we get? Our equation become PH0 as it is plus PB0 minus PH0 into XB. Okay, second term is written initially, this taking XB common outside the bracket, so we write the new equation 2.4. So because of PH0 and PB0 are constant, a plot of pressure versus mole fraction of B component, that is XB, is a straight line. So figure also shows that the plot of partial pressure of A component versus mole fraction of that A component and PB versus XB according to equation 2.2. What is equation 2.2? Here equation 2.2. Okay. So on y-axis we kept vapor pressure, on x-axis we kept mole fraction. At initial state, let us, the mole fraction of component A is 1 and that of B is 0. At this level, the mole fraction of that component A becomes 0 and B becomes 1. Okay, so vapor pressure of that A component, which is denoted by 0, is PA, and that of B is PB0 is here. Okay, now PB means partial pressure of B component is equal to vapor pressure of that B component into mole fraction, and partial pressure of A component is equal to vapor pressure of that A component into mole fraction. Okay, now let us discuss the explanation. When XA is equal to 1, PA is equal to PA0 into 1, and that is nothing but PA0. Where XA is equal to 0, here XA become 0, so we can write here instead of here 1, that is 0. Okay, make it correct, so overall value become 0. Okay, thus so it is corrective. Thus the vapor pressure of such a solution is higher or lower than that predicted by Raoult's law. At one state it is higher, while at another state it is lower. So you can check in your graph. Similarly, you can write for another component. So when the liquid is pure, that is when the mole fraction of that component A is equal to 1, then we say that liquid is pure and its vapor pressure is equal to PA0. Okay, as component B is added to component A, okay, as B component is added to component A, That means initially that A component, which is a liquid, is pure, so mole fraction is 1. So as soon as you added B component into A, the XA value, that is mole fraction of that A component, undergo decreasing, and the vapor pressure also decreases till it becomes 0. So here your partial pressure of that A is nothing but vapor pressure of that A, but as soon as you added B, that means your XA goes on decreasing. When it becomes 0, then here you have to write 0. That means your vapor pressure of that A also becomes 0. Okay. Similarly, you can write for B component. So variation of partial pressure of component B, that is PB, with its mole fraction XB, it is represented by plotting the graph. So when XB is equal to 0, then what is the partial pressure of B? Pressure of that B into mole fraction XB is equal to 0, so you got 0 value. And when XB is equal to 1, then what do you write? PB is equal to, that is partial pressure of B is equal to vapor pressure of B into mole fraction of that B, that is XB is equal to 1, so we get PB 0. So with the help of this, we can write the total vapor pressure of solution, that is P, exerted by that solution as a whole at any composition is given by the sum of partial vapor pressure according to Dalton's law of partial pressure. So P means total vapor pressure is equal to PA plus PB. So composition of, next is composition of vapor pressure and under vapor phase. So composition of vapor phase in equilibrium with the solution is determined by Dalton's law of partial pressure of the component. So Y and YB are the mole fraction of component A and B in vapor phase. Then what do you write? PA is equal to YA into P and PB is equal to YB into B. Okay. Then PA and PB are partial pressure of two components A and B respectively in the vapor phase, and P is the total vapor pressure of that two component. Okay. Now next one is ideal and non-ideal solutions. So first let us discuss what is ideal solution. So ideal solutions follow Raoult's law over entire range of concentration. So the enthalpy of mixing of two components should be 0. That is delta H of mixture, or that mix is written for mixture, it is equal to 0. So this signifies that no heat is absorbed or released during the mixing of two pure components to form a ideal solution. That's why delta mixture or the two solution, that is enthalpy change is 0. Volume of the mixture is equal to 0, that is delta mixture volume is equal to 0. This means that total volume of solution is exactly same as the sum of volume of solution and solute. So delta V total is equal to volume of that solute plus volume of solution. So there will be a concentration, contraction or expansion of the volume while mixing of two components is taking place. Then the solute-solute interaction and solvent-solvent interaction is almost similar to the solute-solvent interaction. Three types of interactions are there: solute-solute, solvent-solvent, and it is equal to solute-solvent interaction. So which are the different examples of ideal solution? So N-hexane, N-heptane, these are ideal solution. Bromoethane and chloroethane, benzene, toluene, CCl4, carbon tetrachloride, SiCl4, silicon tetrachloride, chlorobenzene, bromobenzene, ethyl bromide and ethyl iodide. These are few examples. Here we have to discuss non-ideal solutions. What is non-ideal solution? The solution which does not obey the Raoult's law at every range of concentration and at all temperature. So the enthalpy of mixture, delta mix of H is not equal to 0. Delta V mixture is also not equal to 0. That means volume of mixture is also not equal to 0. The solute-solute, solvent-solvent interaction is different than that of solute-solvent interaction, which is same in case of ideal solution. Now, which are the examples of non-ideal solution? Here some examples. Acetone, all familiar with that. CH3, COCH3 ketone, and carbon disulfide CH2. Then another example is acetone benzene. Benzene all of you know. Carbon tetrachloride CCl4 and chloroform CHCl3 or toluene. Toluene means when we replace one hydrogen of benzene ring by CH3, then we will get toluene. All these things we learn in halogen derivatives. Then methyl alcohol and water, acetone and ethyl alcohol, C2H5OH. These are some examples of non-ideal solution. So non-ideal solutions are of two types. First, non-ideal solution showing positive deviation from Raoult's law, and the another one is non-ideal solution showing negative deviation from Raoult's law. So let us discuss the positive deviation from Raoult's law. So a positive deviation means that there is higher than expected vapor pressure above the solution. So again we'll discuss that previous graph of vapor pressure against mole fraction. So partial pressure of B, and this line is partial pressure of A, where PA0 and this PP0 are the vapor pressure of your A and B respectively, then this dot, so this is the deviation and actual line is shown with dotted lines. Okay, so the solution in which solute solvent intermolecular attractions are weaker than those between solute solute and solvent solvent, so that's why it is called as positive deviation from Raoult's law. And what is negative? These lines are below to the actual lines, and negative deviation means that we find a lower values than the expected vapor pressure for solution. Okay, and the solution in which solute solvent intermolecular attractions are stronger than those between solute solute and solvent solvent molecules.